Okay. Good morning, good afternoon, and good evening to everybody out there in YouTube land. Thank you for joining session number two of the day one of the J Champions Conference. I'm happy to be here with Andre, who will present uh, Scooby RAM, Where Are You? So, of course, the first thing, having been around a long time, I think of Scooby Doo. So, I'm sure that was the inspiration for the title of your talk, Andre. So, without further ado, Andre likes distributed systems in all shapes and form. He's been coding since the age of 8 and loves the simplicity and continuous delivery. While he has written in many languages, he favors the JVM. Since most software problems are people problems, he stirs communities, organizes, and speaks at conferences, and is proud to be a Java 1 rockstar. He is passionate about all things data because science. In his spare time, cycling, photography, and books, and of course, he is a Java champion. So without further ado, Andre, please take it away.
Thank you, Michael. Hello and welcome, everybody. This is my talk, Scooby RAM, Where Are You? If you know, you know. If you don't, obviously it's why it's about RAM and where did it go. My name is Andrzej Grzesik, which is very easy to say if you know how to say it. I also go by Axe because it might be not. I'm a co-founder of a startup called Data Links, where we're trying to solve the problem of context for AI. I have a Twitter, I have an email, so if you would like the slides, that's absolutely doable. Drop me an email with some feedback, and yeah, you can get that. Some things about me, as Michael already said, Java 1 rockstar, Java champion. Obviously, this is a Java Champions conference after all, involved in some user groups. And I also like memes, and I put the memes in my slides for two reasons. So that somebody can smile, and also so I remember that I have to drink, because if the meme is very dry, then I know what to do. Now, since this is all virtual, I will not see anybody waving. I should slow down. So if you have a question on chat, feel free to write it. If I see it, I'll try to respond. If not, we'll try to cover whatever I missed at the end. Now, let's start with some more dryness. So, to memory. We are going, obviously, to talk about memory. And the first thing and first concept that we should consider is, where do bytes live? How is it that we can read something from memory? Obviously, they live in sticks of RAM, which are somewhere on the motherboard, within the computer, maybe within the data center, maybe under your desk, maybe in the cloud. Okay, physically the other. How do you read 1 byte? Well, the trick is that you don't really read just 1 byte. You read and interact with memory through something called cache lines. And cache lines it depends on the specific hardware that you are using, but they could be 64 bytes, for example, here, which means if you want to read just 1 byte from memory, you would take that cache line and then you would mask it so that you can get the byte that you want, which means the interaction with that physical bit of hardware is not at the level of a single byte, but a chunk. And that has some interesting consequences, especially coupled with something else that I'm going to talk about later. So the first obvious takeaway is a single byte. It's almost an illusion. You don't read one. You don't read 1 byte, you read more. But let's look at some specs. Those are screenshots from Intel Arc. Intel used to publish lots of details about their CPUs. They still publish. That's a very useful site. It has information about lots of CPUs, not all of them, because sometimes you might get a device that's not publicly mentioned. What can we see here? Well, we can see that something had 10 cores and could do hyper-threading, so it could support 20 threads in 2013. And then in 2014, number of cores and threads upgraded to 14 and 28. We can also see that memory bandwidth has increased slightly. And you can see that if you do memory bandwidth per core, it actually decreased. which means, that's surprising, or at least it was to me. Cores are increasing in count, memory bandwidth is not. Okay, let's have a look more into the future. A reasonably recent desktop CPU from year of 2021, so 7 years later, still around 6 gigabytes per core of bandwidth. Somebody could say curious. Is that a trend? Is that an odd thing? Excellent question. Actually, there is something called the CPU performance memory gap. And that's the phenomenon that CPUs increase in performance very fast and memory performance grows somewhat slower. There is a gap. Of course, there are many different things that are being done to address this. It's not all terrible, but it's a fact. Memory bandwidth is not growing as quickly as CPU and core counts especially. So some of the effects, well, we have DDR5. Sometime into the future, we'll probably end up with DDR6. DDR5 has more bandwidth, has lower power consumption, which is somewhat relevant when you're on a desktop. It's extremely relevant if you're wondering and worrying about servers, maybe something powering AI workloads. Another effect is if a single RAM stick has only so much bandwidth that it can support, maybe we can interact with many at the same time. So memory channels are a thing, and modern CPUs support many channels. If you remember dual channel, that's that thing. Now, modern server can easily go through 12 channels, maybe even more. One unexpected thing that I was surprised is the website that I quoted at the beginning. Some of the more recent CPUs did not have memory bandwidth published anymore. But also, because the year is 2026, and our favorite AI is everywhere, it had an interesting effect on memory prices. I will not make any commentaries about why this is happening, but right now we are observing a surge in prices of memory, and we will most likely continue to observe that. That will, to us, people who deal with software, have very interesting consequences. I hope that people will actually start caring about efficiency and memory consumption of their software, but also, well, if you need to buy a computer, it might become more expensive, but a desktop is a one thing. If you have a bunch of servers that you need to provision and they need a lot more memory, that will be much more expensive. So people will hopefully look at memory consumption. As I'm saying hopefully, I don't fully believe it deep inside because some people are never going to care, but you're here, so you care. So that's great. So in Java, we have an amazing thing. The amazing thing, or many amazing things, but one of the amazing things that I would like to focus on is called garbage collection. Garbage collection is this magic thing that looks at memory of the process, identifies what's not used anymore, and deletes it. Or if you've programmed with some languages that do memory management by hand, it is there so that we don't have to do delete by hand, which is amazing, at least for some cases and some people. Nah, dry joke, of course. But if we're talking about Java and memory usage and so on, you probably have seen this one. I would call it the very classic one, Java lang out of memory error, Java heap space. Why does it happen? Well, because there is no more heap available, and maybe you're trying to allocate something new. Well, probably that, and that's failing, and there is no more space, so that's the error. Why does it happen? We obviously know about the failure, but if we would like to look at why are the settings and the limits for the heap what they are, then the first thing that I have to mention is something called JVM ergonomics. This is what JVM will set itself to if you don't tell it otherwise, how it will tweak and set GC and memory settings, and it will look at the available hardware, so it will try to take that into account. And if we, for example, look at JDK8 and if you have something referred to as a server class machine. And server class machine, according to JDK 8 docs, means 2 or more physical processors, 2 or more gigabytes of physical memory, which means I here have a server in my hand. Then this is going to set initial heap size to 1/64, maximum heap size to 1 to a quarter of available memory, and so on and so on and so on. JDK 11 changed that. Modern JDKs have also changed that. They keep adjusting. JDK 11, for example, will choose G1 if there is more than this amount of RAM and more than, or at least 2 cores. Good question. What is a core? Because if you're running on a desktop, that part is easy. But if you're running in the cloud and there is, I don't know, some scheduler involved and there is quotas and allocations, shares involved, well, then the rule of thumb is 1,000 millicores, sorry, translates to 1 core. Okay, how does it map to hardware? Well, that part starts being very tricky, and I will not go too far. But for example, in Google Cloud Docs, I found that Google Cloud instances have 2 vCPUs, so virtual CPUs, per a physical core by default, which means that's like hyper-threading. So the fact that your VM tells you that it has 20 cores does not mean that it's running on 20 physical cores under the hood. It might be different, and it varies, and you have to check. Why do I mention that? Well, because there is more. Because if we're talking about containers and running in the cloud, and probably most of you are running in the cloud, I definitely am myself, then applications get something called CPU quota. And this is the total amount of CPU time that a container can use in each CPU period. As you can see, 1 core in a CPU period, but it doesn't say that it's 1 core per each CPU period. It might be maybe 2 cores in half a CPU period and then nothing, as long as that is satisfied. So multiple threads might run in parallel. If you don't do anything to help, Kubernetes can't really tell application and GC and other JVM internal threads apart, which means, yes, they are also running there. There is garbage collector that runs there, and that might be taking the cores that you would otherwise want to dedicate to your application. Luckily, it's all not doom and gloom. And if we look at JVM ergonomics, JDK 11 onwards, this looks familiar, I would say. Server or defaults will be initial heap to 164 again, maximum heap size to a quarter of physical memory, tier compilation, G1 garbage collector, and so on. That's okay. If you're running Docker, I assume everybody here now runs a reasonably modern JDK, then JDK has support for that through those options. And why do I mention this? Because this affects thread pools. Why thread pools? Because, well, threads cost memory. We'll talk about that later. But because if you're running in containers, you might want to express your memory consumption or appetite for a container, not as a specific value, but as a percentage of the container size. Should you? It depends. I prefer to actually specify for any kind of machine or kind of machine that's code I would work with, would operate in, to a specific value. So I don't have to do the percentage calculations and I know exactly how much it should be, but you can. If you maybe want to experiment, maybe you will keep letting somebody else grow something continuously. Maybe that's a thing. This is available. There is also an option to set active processor count. So if you want the JDK to behave like if the number of CPUs was 7, you can. And you can see that, yeah, it can read Docker-related and container-related settings. One observation that I will make here is Java and JVMs in general like more than one CPU because there is this overhead. There is garbage collector, there is the compiler that needs to run, which means doing lots of half a CPU VMs, I would not recommend doing that. I would recommend doing fewer of larger. Also, Java likes what I would call a reasonable amount of RAM. It needs some RAM because garbage collector is a process that runs in the background. It tries to collect, well, filter garbage from something that's alive and still useful objects. It needs some place to operate in. If it's not available, well, it will struggle. Java is usually quite okay in terms of memory consumption, unless, well, the code is doing something nonsensical. But yeah, this is not a great thing if you have 32 megabytes, but if you have, I don't know, more, it should be fine. If you're operating with tiny amounts of memory, Graal might be something that helps you. Now, JVM in a container, we know about this flag. We can set it to something specific. We know that we can tell it how much RAM it should use in two ways, with a specific value or through a percentage. Let's have a look at some code. I'm not going to live run it because life is short and demo gods are what they are. If I run it on a MacBook, or I have run it on a MacBook and made those screenshots, setting nothing, available processors reads 12. If I override the flag to 48, that will be set to 48. Why does it matter? Because thread pools that the JVM will have will be initialized using the number of processors as a guidance. So if you want to ensure some sizes for the default pools, you can influence it in this way. And if I run it through a container and I give Docker 3 CPUs as a limit, and I try to see how many CPUs does the underlying Java process see, of course, that value matches. And then if I try to override it, overridden value takes precedence. Here I will mention print flags final for the first time. This is a very useful thing that tells you the settings that JVM has actually started with. But we'll talk about it later. Here I'm just signaling that it's useful to figure out what exactly is happening. Now, XMX and XMS. What's the relationship? Or if I don't want the heap to fluctuate, should I set them to the same value? Well, a lot of people say that yes, you should. And I would say yes, because in most cases, I want to have a predictable amount of memory, and I want to know that this is the amount I've given to the JDK, and this is what it's running with in terms of heap. But this is not enough. You also need to add 2 extra flags. One is called pretouch, because Linux is great. It's awesome and it's lazy, and it actually gives memory pages when they are used. So if you say, hey, I want 7 billion gigabytes of RAM, and you never use it, yeah, sure. We can pretend that you have that. And if you actually start using this much, we will worry then. And then there is a second thing that you need to disable, which is called adaptive size policy, so that the JDK will not try to give memory back to the OS. Always pretouch, as discussed, and as discussed. But there is more, of course. You remember that problem of out-of-memory error. And we, of course, are dealing with Java, running in Kubernetes, maybe in one of the cloud providers. Well, first comment I will make here is I usually stick to glibc-based containers because I have less problems. I've never tried to aggressively optimize Alpine-based one, or to use Alpine to optimize aggressively, so your mileage might have been better or might vary. But I keep using glibc because it usually gives me less problems. But in Kubernetes, there is something that's called killer. And here I would ask if anybody in the room has seen it, and can you wave your hands? And then some of you might do that. So have you ever had a container die on you? Maybe. So we will talk about some things here so that we can see what's possible, why it might have happened, why could have a container been killed, and which of those colorful rectangles might be associated with that. So we'll talk about heap, we'll talk about metaspace, we'll talk about off-heap, we'll talk about code cache, we'll talk about thread stacks briefly, and we will not talk about symbols. So let's start with heap, the classic. Java heap, the one that you set with XMX, That's usually the major pool of memory available or used by a Java process. But every heap, every garbage collector algorithm needs some overhead to do the bookkeeping. How much? It depends. I will not give you a specific percentage. I will use a screenshot from a specific workload from a Java 1 talk, and there is a link down there at the bottom if you're interested. So, for example, for that workload and that heap, there were varying overheads or peak native memory overheads. What is it going to be in your workload case of your workload? I don't know. Probably measure. But looking in here, as in it's usually roughly around 1,000 megabytes, maybe between 1,000 to 1,500 for a 16 gig heap. So 10% or less as a rule of thumb, very imprecise, but it's something to think. Okay, heaps. If they run out of memory, what do you want to do? Well, you would like to have a look inside and see why it failed. How do you take a heap dump? I don't have an interactive way of interacting with you, so this will be a quiz without prizes. One of the options is, for example, heap dump on out-of-memory error. You can ask the JVM to produce a heap dump if it encounters an out-of-memory error. Great. You can even ask it to compress it. You can do it through something awesome called JCMD. And here we have an almost live demo of how you would do it. You list the processes. You ask JCMD for what are the options available within that process, as in GC heap dump is the one that we're after. And then we say JCMD, this process, GC heap dump into that file. Easy. This will take some time, and this will take some amount of memory. And I mentioned clouds and orchestrators, right? So there is a couple of caveats. First of all, if you're running in a container that has no space where to produce it, you need somewhere to put the bytes. Larger heap dumps can be large, no surprise here, which means you might need to attach a volume, you might need to do something. You might want to put it on S3, you might want to put it on Google Drive. I don't know. It really depends on your specific case. But also, if you're doing a heap dump, your application is not going to be terribly responsive, which means if you expect it to respond to a health check, a heartbeat every second, or maybe every 2 seconds, and it can only miss 2, and you're producing a large heap dump and you have to transfer this data to an external drive or external storage, it might get killed before it succeeds, which means there is maybe some choreography that you will have to look into. So yes, in Kubernetes or in something else, maybe take the machine out of the health check, disable it, attach a volume or do something. But there is another issue. Heap dump has all of the data that's in the heap, which means there might be private data. Private data, if you're doing that on dev, that's probably not going to be terrible. But if you are working in an industry that cares about privacy and data, that can raise some eyebrows. Luckily, there is a tool for that, or there are many tools for that, but one of them I will mention is something that's coming from PayPal, which is very interestingly called heap dump tool. It's one of the things that it can do is it can sanitize private data, and you can tell it what private data looks like so it knows what to do, so that you can actually have a heap dump that you can investigate, or other people can investigate, give it to people to investigate, but with things that you want sanitize. So you're not going to hopefully leak emails, passwords, and so on and so on and so on. Okay, I think taking a heap dump is quite straightforward. What do you do with one? Well, you open it in any of the tools that you know. I mentioned a bunch. This list is definitely not exhaustive, so there are more tools that can deal with a heap dump. Pick any or pick a few. But before you do, or if you do, or with whichever tool you pick, I'll mention a few things. A heap dump from, for example, a 16 gigabyte heap will likely be larger than 16 gigabytes because the class information has to go somewhere, and some other, well, stacks and threads and so on have to go somewhere. Your tool for a larger heap, loading a heap dump might take a while. Can be half an hour. For something very large, sometimes you need a machine that matches the production grade server that you're running on, because maybe it has, I don't know, half a terabyte of memory. Sometimes you will need to adjust the memory options for the tools that you're using, and some tools sometimes fail on some heaps. To me, that's normal, but it might surprise you. So if one of the tools fails, try the other. This is why I mention a few. Now, what can a heap dump tell us? There is a number of standard things that probably any of the ones I listed can give you. For example, an overview. What are the biggest objects in a heap dump? As in, that heap dump is not terribly useful, but we'll have a histogram. So number of instances per class, what are the biggest objects, what are the most expensive objects, duplicate classes, maybe string deduplication. There is a number of reports that almost all, if not all, tools support, and then they will differ by how they present it in the UI. So if we, for example, open the Eclipse Memory Analyzer, which is free and open source, which is why I can safely recommend it, you can see output from it. You can see that, hey, there is a thread that is a GC root that has so many strings associated with it, and the retained heap is over a gigabyte here. The details don't matter. What is interesting is, or not interesting, what's relevant is most of tools will allow you to surface the same information. So it really, the choice doesn't matter, just pick the one that you like. But I will mention here something very interesting called Joel, which is a repo inside OpenJDK, which has a bunch of command line tools that allows you to analyze a heap through command line. So terminal, if you don't need a UI, if you're happy with working with strings, you can, for example, get information like that. How many duplicate strings are there in the heap? What's their size, and so on and so on. The reports, again, duplicate strings in another tool. This time it's a screenshot from your kit. This is a screenshot from Joel doing class histogram. So as you can see, this is equivalent, if not the same. And I could do a quiz time, and because we're very interactive, the question would be, can you see a leak? And this is one of the tricky leaks, which is because somebody did JNI, but they did it poorly, and they did not actually release the local reference, which means they were always allocated, which means they were always held and never released, which means GC could never get rid of those strings. But if you don't touch JNI, you don't have to worry. But one interesting thing that has become available recently, and here is another opportunity to ask which versions of the JDK are you on. If you're on JDK 24 and upwards, you can use something called compact object headers. In JDK 24, that comes through two options. In JDK 25, just a single option, which reduces the memory pressure that object headers in some situations have, which basically reduce the amount of memory needed. But Java is not only heap. There is more. There is more reasons why this could, where something could fail. Let's have a look. Metaspace. What is metaspace? Well, class files or class data has to live somewhere. You set the size using a flag, and you're good in most cases. As in, setting it to a known maximum has the benefit of, if you ever cross that maximum, you will get a failure, which means you need to tweak it, and then you don't have to guess about how big it is. I prefer that approach to just letting everything dynamically reconfigure, and if there is a problem, I have to figure out what the settings were. There is also off-heap memory. Off-heap memory, byte buffers. Byte buffers, their default size limit is XMX, so the heap size. You can see how many and how much memory through, for example, through MX beans. but that memory is not on the heap. So that's the beauty of it. This is what will not be touched by garbage collector, but it also means that you have to, well, worry about the bytes that are inside there. How do you see? Because maybe they could be leaking. Maybe your Kubernetes, maybe a container has been crashing on you. You have a couple of options. Java has built-in native memory tracking, which allows you to track allocations in the JVM, which means if there is third-party JNI in native code that is on the path of your application, maybe you're interacting with something in C++, you're not going to see it. There is some performance penalty related to using that. But if you have nothing, well, that's a start that's available to you. If you can, I would say the best tool out there to figure out native memory issues is Async Profiler. It can record JVM, JDK, and third party, and all kinds of information. So if you have a free choice of tools, pick that one. If you don't have a free tool choice, maybe you're in a limited environment. Maybe it takes half a year for some people to process a request to install something somewhere. At least that option is in the JDK built in. If you're doing that in dev and you can experiment and you like experimenting, you can also use gemalloc and ask it to track allocations. But as of today, I would absolutely recommend Async Profiler. It's the best. Now, native memory. There are more quirks with native memory. So native heap interval, trim native heap interval is an interval in milliseconds at which the JVM will trip the native heap, which means it's another thing that the JVM will do for you. It will try to trim that heap. Default value, when I checked, was 0. So that means that's not an enabled thing. And this is one of the things that was when I checked running only on glibc. You remember my comment about glibc before. This is one of the reasons. It is performed in a dedicated thread, which means, yes, those CPU limits maybe in a container might be a thing. You can also ask the JVM to do it by doing JCMD. Okay, but also there are threads, especially after 21. There are threads which are virtual. Some people say that all threads take a lot of memory. Now it has become double untrue. It used to be, it depends. So first of all, the great thing about yet another great thing about Linux is native thread memory consumption will depend on the stack depth. If you have very short, shallow stacks, threads will not take so much. That's one important thing to remember. Second thing is virtual threads. So the thing that Loom brought us, which you might be using in 21 and onwards, they store their state on heap. So this is not going to be now in native memory, which also means that the pressure is now moved to heap, which means it's going to be putting pressure on garbage collector. You can see how it's all connected. Symbols, one thing that we will not talk about. And then I'll mention code cache. And I'll mention code cache because this is the area of memory that the JIT compiler uses to convert Java bytecode into native code and do all of the optimizations in there. Defaults are as on the slide. Why do I mention this? Because if an application that has a lot of code that's running for a long, long time, you might run out of this code cache. If you run out of code cache, that will come with a performance penalty. No new method, no new code will be optimized anymore. That would be quite sad. Nobody likes slow software, I think. Except for some people who program in that programming language. Wink, wink. What you can do, for example, is print the code cache memory usage when exiting. And I mention it because if somebody is on the recent JDK, specifically 25, there was a regression that affected code cache, which has been fixed or backported into 25.02, which means if you're on 25, make sure that you're using 25.02 or later. Otherwise, you might suffer from it. Might, not will. So we've looked at some kind of an overview of those areas, except for symbols. But why? Well, because we know that memory throughput is limited in bandwidth, and there is a gap. And with that comes a connection to application throughput. Application throughput is time your application spent running application code. What I mean, not running garbage collector code. So you might see an application that, for example, is pausing for some amount of time, as in those red dots are pauses. If an application is pausing regularly for some amount of time, that's quite bad. That means application is not working, not being useful, because GC is working. GC is doing its job. It's absolutely fine. There is nothing wrong with it. It's just something has led to that situation, and that is unfortunate. In the tool that's no longer sadly available, JClarity Sensum, there was a way to chart full generations in a very easy way. You can get to the same chart using different tools. And with that, there is another error, which is a Java lang out of memory error called GC overhead limit exceeded. Here again, I ask, who has seen it and who has dealt with that? And I see lots of hands, great. How often does it happen, or what's the limit? Excellent question, my dear audience. If we use our favorite XX print flags final, we can easily see that there is a thing called GC time limit, which is 98%, which means a garbage collector can spend 98% of time working and everything is fine. Which means if your application is running 3% of the time and 97% is dedicated to GC, Java will be happy. Only if it crosses that threshold, is going to throw that. You can disable that. I don't think you should. But especially surprising is the default, which is 98. If you're spending lots of time, as you probably have seen that application just feels like it's not being very responsive, and then it works for a bit, and then again and again and again. Maybe GC can be working with a very full heap, and it's trying to do whatever it can in the limited free space that's available. This is why, or this is a situation in which you could see why maybe increasing the heap would be a thing to do, maybe something else. And yes, that one. How do you know that you have problems leading to those errors? How can you see those problems before they happen? Well, the answer is very easy. If you know it, you enable GC logging. That's something absolutely safe to do in production. For those of you still on Java 8, please upgrade. But if you can't, this is one of the ways to do it. Java 9 and onwards, this is an example way to do it. I am not going to tell you all of the options. There are great books about it. Some more screenshots for people in legacy enterprises. If they can migrate, good luck, have fun. So let's assume we have a GC log. What does it look like? It will look like something like this, or maybe this. Don't try to read it by hand. There are many GC log analyzers out there, and the story with them is similar to heap analyzers. Just pick whichever one you like. And also this list might fluctuate. Some of them might disappear. Some of them might not support the version of Java that you want to use. Some of them might not, correctly parse. See what's out there. What are they going to tell you? They are going to tell you what kind of behavior, what work a garbage collector was doing and how busy it was. If you can see that it has only a very small amount of free space that it's trying to work with, maybe it's time to increase your heap. But rather than passing the work onto garbage collector flags, I would encourage you to do something about the code. And we'll look towards that area very soon with two most popular examples out there. First of all, flags and caveats. I mentioned print flags final before. So here it gets its dedicated slide. Why do I mention this? Because if you start setting flags, they can change between releases. They affect each other. There is a lot of them, and nobody expects you to remember. A great resource, a great overview, a list of all of them with some descriptions, with defaults, when are they applicable, is a website, Critical Codes. There are many JDK versions and vendors listed there. Of course, if you really like reading code, you're absolutely welcome to read the JDK sources and figure it out for yourself. But if you need to pass a link to a colleague, that website is amazing. For example, if you try to look for on out of memory error, we can see crash on out of memory error, exit on out of memory error, heap them on all of the things as you would expect. Why is that important? Because some flags might trigger changes in others. Some might conflict, some might override. In order to know what your application actually started with, you have to see what you have to use this. Just looking at the start script might not be enough because there might be something that had an unexpected interaction. So let's say application is slow. There is something that we can do to the RAM. Maybe there is something wrong that we are doing or somebody else did to the RAM. And what are the most common cases that I've recently seen? And there are specifically two. First of all, heap can have lots of strings. We all do JSON. JSON under the hood means strings. If you process JSON input, massage it, and then process JSON output, you will probably end up with a heap full of Java lang strings. That's absolutely normal. What happens if your heap is too full? Well, you have a couple of options. One of them is called string deduplication, which is built into the garbage collector in the JDK. And G1 and ZGC can deduplicate strings, and it works. But there is a catch, or there is a caveat, or it might be useful, but I will not encourage you to run it in every single production application after you learn of this flag. Why? Because two things. First of all, there is string deduplication age threshold. So an object has to pass through a few collections in order to be eligible for this. Second thing is it deduplicates the underlying array, which means the string object, the header, and so on, that will be repeated. It's not going to be a silver bullet. If you get a random spike of requests, it's not going to immediately kick in and save you. On the other hand, maybe if you have a very long-running application that has a lot of memory, maybe that's going to be useful. What should you do? Benchmark. Okay, if that's not great, what else is there that you can do? Great question. You can pull strings. And here, the audience is asking a great question. Which strings? You've seen that tool before. You've seen many tools before. Tools, heap analyzers, can usually find strings in a heap dump that are replicated, that there is a lot of duplicate of them. That means how you should go about it. You take a heap dump, you see what's inside it, you see which values are repeated many times, and some of them there will be a point in pulling, some of them there will be no point in trying to get rid of. Use your and your colleagues' expert knowledge of the codes and behaviors and see what actually matters and see where you can reduce the pressure. Another example of things that's very popular, it's primitive collections. Java lang double, Java lang long, Java lang integer, and so on. Because we know that we cannot put a lowercase long into an array list. We have to do this. This has with the added overhead of there is an object, header, and then there is the value, which is the primitive, which sits in the collection. How big of an impact is it? Sadly, the answer is it depends. It can be a small, negligible one, it can be a tremendous one. Rule of thumb is if you have very large collections with lots of numbers, then probably that's something that you will want to look into. If you keep 5, 10, 20, nobody cares. So an example workload, which I'm not going to show you the code for because that's not the point. Some code doing some work. The workload took 120 seconds. Allocated megabytes at the end was almost 1900. That code has been changed to an array list, to a long array list, so a specialized collection from FastUtil library. That has reduced the allocation pressure to somewhere under 1800. Doesn't matter exactly how much. Now you can think, how much could that have impacted the runtime? And before you say, yes, you should do it always, or it doesn't really matter, the problem here is it depends. It might be something that's very relevant to your application. It might not. You have to run your own benchmarks. But in that case, that specific workload, for small arbitrary something called input size, it could have sped up something that could take 240 seconds down to 160. So over a minute saved, or for larger workloads, which would take 769 seconds, down to 513. Wow, that's a significant change. Why is that? Well, garbage collector has to visit objects, see if they are still relevant. We know about that. But also because we allocate less, we put less pressure through that very limited pipe of memory bandwidth that we know about from the very beginning, that also has an impact. I cannot promise you this is going to be applicable to your cases, but give it a look. Have a benchmark, see if it works. Some examples of specialized collections. I will mention Eclipse because it has a nice logo, and some other. This list does not claim to be exhaustive. There might be more. You probably don't want to run and write your own specialized collection unless you want to learn the details. There are very good examples out there. I like Agrona. I've used FastUtil before. A lot of people are using Eclipse collections out there. They have something that works extremely well. There are other options out there as well. It might be useful for you. It might not. Now, let's move on. There is something in the JDK which is called Epsilon, a no-op garbage collector. What do I mean? Well, it's a garbage collector that does, as the name says, it does nothing. You enable it with that. Does anybody ever use it? Excellent question. Yes, absolutely. For example, in the 1 billion row challenge, some people, well, quite a lot of people have been very successful using Epsilon GC. And here you could ask, is it faster? Well, theoretically, or on one hand, if there is no GC work being done, everything should be faster because you just don't have to execute that code. You could be right, but you could not. If you allocate very little, then there is not a lot of memory to traverse. But if you allocate a lot, not only heap might run out of space, but also you have to traverse through much more memory, and that traversal is limited, as we know from the very beginning. Why do I mention that? Because you might want to, in some specific cases, you might need to see how long your application is going to run, how much it's allocating, and have a way to benchmark us. And have we improved? Have we not improved? And there are two things that you can do. One is called allocation profiling, which will happen in a second. And the thing number 0 is you can run it with a GC that does nothing and measure operation count that was successful, or maybe time, whatever works for your app. So allocation profiling, using the example of Visual VM and or NetBeans profiler, because the component is the same. This is how you do it. You click there, well, pick the application that you care about, you click on profiler, you click on memory, and you say what you want, and then you wait. The caveat is this will be slow. You probably cannot run this in production, but it will tell you where you're allocating objects. There's something better that you can do that you've already heard about today, which is async profiler. You can use it in prod, I would say even. And Why do I mention that? Because this is where you find where you're producing objects. If you know that you're producing lots of objects somewhere, maybe because you're receiving lots of JSON objects, maybe you can do some smart string pooling there. Maybe those are JSON maps, and maybe you can reduce the pressure on even just the keys on the map. Maybe that's a place. But as somebody already commented in the chat, it's like consulting. It depends. Your mileage will vary. I mentioned things that might be useful to you, hopefully will be useful to you, but you have to run your own tests. There is no magic wand that you can wave and say, hey, this is definitely going to work in our case. It might not. Ideally, you should run your benchmarks. You should have an isolated environment, at least similar to target. And you should also try to design experiments that will prove that or verify whether the experiment that you're running actually makes sense. Because if you try to do something nonsensical, well, the numbers will come out. And the question is your whole thought process working correctly? So what I'm saying here, there is no jumping to conclusions. This can be difficult and complicated. And it's normal. And the best thing is to ask and talk to your colleagues and talk to people you work with. So, and somebody commented that if it was always better, it would be part of the default. Yes, that's an excellent comment. I completely agree. Java is evolving. They are changing some of the defaults, but there is a lot of diagnostic options available so that you can tweak your workloads to whatever you need. Now, I can say thank you. I can imagine everybody clapping, and you can imagine me bowing to you on the stage. If you need a few slides, easy, drop me an email. You could ask a question of, for example, when would I tune? If you need to tune, or when you have a very specific goal that's usually aggressive and you cannot really change the code and you have to get a result, and then probably this is where you would look at all of those levers, because the mass that you're dealing with is unmanageable. Maybe the code base is complicated. Maybe you have a very short time in which you need to get results. Maybe you're preparing for a cyber retail event. I don't know. The caveat is you need to know how to tune. There is a lot of gospel out there. And the great thing with AI is it has gone through and been trained on lots of posts on all of the available and no longer available media out there, which means it has also accumulated some information which is no longer true, which means what should you use? Well, one safe example is this one. And as you can see, Java performance has been a problem for many, many, many years. But I can absolutely safely recommend this one. There are more books about Java performance. If they come from good authors, you can probably safely go there. Do I see any other questions in the chat? Let me scroll through the list. No. I don't. And I still don't. And I still don't.
Josh commented about 20 minutes ago that off-heap memory is his favorite. I thought that was, I like that one.
Oh, I like off-heap memory as well. The problem is when you make objects, they don't end up in off-heap, so you have to manage that. If that's what you want, then it's great. But if it really depends again. So if we have no more questions, then we'll finish here. I will say thank you very much. Enjoy the conference with definitely the biggest amount of Java champions or the biggest percentage of Java champion speakers out there. Michael, thank you so much for your assistance. Everybody who wrote something in the chat, thank you so much for being here. Hope you enjoyed it. If anything, drop me an email. Have fun. Keep well. Bye-bye.
Okay. Take care, folks. Thanks for joining us.